As human beings, we are constantly concerned about uncertainties. We constantly ask ourselves questions that do not have certain answers at the time that we ask them. Just to give you some very simple examples. Is it gonna rain tomorrow or not? Or as a second example that a lot of Americans are thinking about, if I send my kid back to school in the fall, am I gonna get the new coronavirus? Or suppose you're playing a game in which you roll a die. What will be the number that you get from rolling the die? Lots of uncertainty. Gets resolved in the future. That is, in a exposed stage. But we want some kind of answer before the uncertainty is resolved. That is, we want to answer the questions in some way in the ex ante stage. So probability theory is a tool that helps us to answer these questions in the ex ante stage. Probability theory quantifies uncertainty, and by quantifying the uncertainty, it helps to guide our decision in the ex ante stage. Now, let's consider two examples where probability theory might help you to make a decision. Example 1, camping trip. Suppose you were planning and you're looking forward to a camping trip over the weekend with your best friend. And you want to know whether it is going to rain over the weekend or not. It's because it is not so fun to camp when it is raining. So on the last day that you can cancel your booking of the campsite, you take out your phone and look at the weather app. The weather app tells you there is a 10% chance of raining over the weekend. In that case, most of us would think that the chance of raining is low, so it's probably not going to rain. So we'll go on the camping trip as planned. But suppose the weather app tells you that the chance of raining is 90%. Then suppose it is possible to reschedule your trip. Then a lot of people would say that let's reschedule for next weekend. And suppose it is 50%, then that means there is a lot of uncertainty. We don't really know whether it's going to rain or not rain, but there is a big chance of raining. Then the decision might not be so clear, but the 50% may still guide you through your decision. It might change what you do, right? You might plan to go, but bring an umbrella. Or if it is really easy to reschedule, you reschedule it in this case as well. So that's first example where probability theory guides your decision making. The second example, antibody test. Let's assume that people who have gotten the new coronavirus and recovered from the disease develop antibody that protects them from getting the virus again. right? So let's just assume that we are not medical professionals. We don't know whether that's true or not, but let's just assume that's true. And you want to know whether you have the antibody. Well, this is a very important information to find out, right? Because if you do have the antibody, you don't have to hide in your dorm anymore. You can go out because you won't be infected by the new coronavirus. And if you don't, maybe you should continue being as cautious as you have ever been. So you go to a place to get an experimental antibody test. And it turns out that test result is positive. That is, the test tells you that you have the antibody. How reassured should you be? But this depends on a bunch of stuff. It depends on, for example, what is the accuracy of the test? Now let's assume this test is accurate 99% of the time in the presence of the antibody. And it is 80% accurate in the absence of the antibody. That is, for 100 people who have the antibody, 99 of them will be tested positive. And for 100 people who do not have the antibody, only 20 of them will be tested positive. Okay, 80 of them will be tested negative. This looks like a good test. But just knowing the accuracy of the test is not enough. And to answer your question, you also need to know what's the prior probability. And let's suppose that 1% of people in Dane County, which is where you live, have the antibody. This is also a piece of necessary information to do your calculation. What is the probability that you have the antibody? Okay, I'll give you several choices. A, 80% to 100%. B, 50% to 80%. And C, 20% to 50%. And D, below 20%. Now remember, this is when you have already gotten a positive antibody test. What is the answer to this question? So we're not gonna do the calculation now because we don't have the tools yet. I will tell you the answer. The answer is less than 5%. Really, you should not be very reassured by this positive antibody test result. And as we learn more of probability, we will be able to calculate this probability, and we'll know how this is calculated. Now let's begin our study of probability theory. We start with the basic building block of probability theory. The first building block is sample space. What's the sample space? The sample space is a set, and it is the set of all the possible outcomes of the uncertainty that you are concerned about. Typically, we denote the sample space by S. S is the set of all outcomes of the uncertainty we are concerned about. For example, if we are concerned about the weather of the weekend, S is rain and no rain. These are the two possible outcomes. That's one example. The second example Suppose you're concerned about the antibody, whether you have the antibody or not. In that case, the S is have antibody and not have the antibody. Or if you are rolling a die, then the sample space is all the possible outcomes of the die roll, which is 1, 2, 3, 4, 5, and 6. Notice that the concept outcomes are the possibilities, and the outcomes are so defined so that one and exactly one of them happens when the uncertainty is resolved. Now, because S is a set, the outcomes are the things that form the set. So each outcome is also called an element of the set. In set theory language, each outcome is an element of the sample space. The outcome is typically denoted the small letter s, while the sample space is a capital letter. For set theory, one useful tool is the Venn diagram. A Venn diagram is basically just a box that symbolically stands for the sample space. Okay, this box symbolically stands for the sample space. And an outcome is a point in this sample space. That's an element of the sample space. If little s is an element of the sample space, we also denote that little s belongs to big S. Now that's sample space. The next concept is event. What is an event? An event, typically we denote it by E. An event is a subset of the sample space, or written as E is a subset of S. This is the subset symbol. In a Venn diagram, this is the box that stands for the sample space S, and a subset of S, an event, is typically symbolically represented by a circle in this box, and that is event. For example, in the weather case, the event of rain is a subset of the sample space rain and no rain. And the event of have antibody is a subset of the sample space of have antibody and not have antibody. And third, in the experiment where you roll a dice, the sample space is the 6 numbers. An event can be all the odd numbers, or all the numbers that are smaller than 3, smaller than or equal to 3. That's an event. Now, because sample space is represented as a set and events are represented as subsets of the sample space, some basic set theory concepts are useful. First, we consider some basic set operation that include union. Suppose that A and B are two events, then the union of A and B is another event, which is the set of all the outcomes in the sample space such that either S is in A or little s is in B. Example, suppose A is 1, 3, 5, all the odd numbers coming out of the dice rolling experiments, and B equals 1, 2, and 3. Then A union B would be 1, 2, 3, and 5. And in Venn diagram, again, we draw a big box that stands for the sample space. Let's say A is this orange colored circle, and B is this pink colored circle. Then A union B is this whole area formed by these two circles, right? This whole shaded area is A union B. That's in Venn diagram. Now the second basic set operation is intersection. Two events A and B, their intersection is also an event. It is the set of all the outcomes that are both in A and in B. Consider the same example as before. A is 1, 2, 3, and B is 1, 3, and 5. Then A intersection B is 1, 3. Now in Venn diagram, this is the sample space, and let orange circle stand for the set A, the event A, and again let the pink circle stand for the event B. Then this area, that is the overlap of A and B, stands for A intersect B. And the third basic set operation is complement. The complement of an event A, which is denoted as A subscript C. The complement of A is the event that's formed by all the outcomes that are in the sample space but not in A. For example, if A is 1, 2, 3, then the complement of A is 4, 5, and 6. That is, if the sample space is all the outcomes from the dice rolling experiment. That's 1, 2, 3, 4, 5, and 6. Now in Venn diagram, if this is A, then the shaded area that's in S but not in A, all the shaded area outside of A, is a complement. Now it is obvious that clearly the union of A and A complement is the whole sample space S. The union of A and A complement is S. An outcome is either in A. If it is not in A, then by definition, the outcome S is in the complement of A. And also we know A intersect A complement contains no element. The set that contains no element is called the empty set. So A union A complement is the sample space. A intersect A complement is the empty set. And it's not hard to see that the complement of the complement is A itself. And when you apply complement twice, you get the set itself. And you can see that clearly from the Venn diagram. Now these are the basic set operations, and there are also some set relationships that can be useful in our discussion of probability theory. First set relationship is disjoint. Two sets or two events, we use the concepts events and sets interchangeably because an event is a set and a set in the probability context is an event. So two events A and B are disjoint if they have no common elements, or in other words, if their intersection contains no elements, is the empty set. If A intersects B, is an empty set. Represented in the Venn diagram, suppose the set A is here, then the set B will be somewhere that doesn't overlap with A. And now clearly we know A and A complement have no intersection. Their intersection is an empty set. So A and AC are a disjoint. So this is an example. A more concrete example, suppose that A is 1, 2, 3, and B, in this case, let's say is 4, 5, 6, then A and B are disjoint. The second set relationship is disjoint groups of sets. Now the first disjoint concept is about a pair of sets. Now let's consider a group of sets, a group of events. Say A1, A2, A3 to AN is a disjoint group of sets, or a group of disjoint sets if any pair are disjoint. Or in mathematics, AI intersect AJ is empty set for all I and J, such that I not equal to J. In Venn diagram, we can draw this A1 to AN like this. Right? It's not hard to draw. Let's say this is A1, A2, A3. This A1, A2, A3 is a disjoint group of sets. The next concept, next set relationship is exhaustive. Exhaustive group of sets. So the group of sets A1, A2 to AN are exhaustive if they exhaust all the possibilities of the sample space. Or in other words, if the union of all of them equals the sample space. That's any outcome of the sample space is in at least one of the events in this group. This long this long expression is also equivalently written as union I from 1 to N, AI. Okay, so this and that are equivalent expressions. So in Venn diagram, we can draw an example of an exhaustive group of sets. For example, this is A, and this is B, this is C. Green shaded area, let's suppose that is D. In this case, A, B, C, and D are exhaustive. So any element of S, it belongs to at least one of A, B, C, or D. For example, this element belongs to D. This element belongs to both B and C, and this element belongs to both A and C, and this element belongs to C. So any element of the sample space, any outcome of the sample space belongs to at least one of the sets in this group. So this group is exhaustive. The last concept of this video is partition. If a group of sets A1, A2 to AN are both disjoint and exhaustive, then this group form a partition of S, of the sample space S. In Venn diagram, we can draw a representation of a partition like this. Let's say this is A. This polygon-shaped area is B. And let's say the rest is C. Let's say the rest is C. Okay, so this area is C. Then A, B, C form a partition. For example, if S is the outcome of a die rolling experiment, suppose that A is 1, 2, and 3, B is 4, and C is 5, 6. Then A, B, and C form a partition. So this is the end of this video. Next video, we will talk about probability measure.